This is the second session of the research papers. We have four that are going to be discussed. Again, if we don't have any objections, we will record the session. So if any of the speakers object to that, just let us know either now or before the talk. Otherwise, we'll assume that that you guys are okay with it, and we'll record, and eventually we'll share the video online. Is it okay with you, Tom? And Wolfgang?
Yeah, I'm fine with it.
So the first speaker is then Tom Krüger, and you will be talking about quantum annealing-based software components and experimental case study with SAT solving. Tom, please.
Okay. Yeah. Hello, everybody. Yesterday we already heard a talk about quantum annealing, and I also will talk about quantum annealing. And especially we looked at using quantum annealing-based software components and did a case study with SAT solving. We used quantum annealing, of course, and the term quantum accelerator picture is unrelated to the keynote, but yeah, it's funny. And as already mentioned in the keynote, quantum annealing is very good at optimizing problems, at optimization problems. And I will note here that the quantum annealing by D-wave is quite controversial, but from an interface point of view, it's not that important. The physical controversy about it. About the content of the talk, we did a case study highlighting some important pitfalls in the process of designing and comparing quantum annealing queries, and also highlighted maybe a difference between required and desired levels of abstraction. Just to go over quantum annealing very briefly, it is, as already mentioned, great at approximating optimization problems. From an interface standpoint, it is quite similar to classical constraint solvers like simulated annealing and SAT solvers, where we also have a native problem where the optimizer is optimizing. In the case of quantum annealing, this is the QUBO problem or QUBO functions, and we don't really have any quantum programs, but we have interface calls to the quantum annealing component via these QUBO functions. Then, what does the integration look like? If we are interested in the solution to our problem or function f, then we have first we have to translate this function to the native problem of the quantum annealer, which is the QUBO function, and then after we can pass this to the annealer, and then we get a result to this QUBO function back, which we then have to translate to a result to our original problem we were interested in solving. So this whole process and integration is quite similar to classical optimization solvers or constraint solvers like simulated annealing, which means that it's quite, from an interface standpoint viewpoint, it's quite straightforward to replace these classical constraint solvers with quantum annealing solvers. But we have two critical stages we have to look into. First one is the problem reduction, where we are interested in a solution to a problem A. The native problem is, the hardware has a native problem Q. Then we have to reduce A to Q and pass it to the annealer. And the second stage, which we don't have at classical optimization solvers, is the process of embedding, because in the case of quantum annealer, we have a hardware accelerator with a fixed hardware structure, and we have to map our QUBO function onto this fixed hardware structure. Then in our case study, we looked at 3SAT. It's a very well-known and well-studied problem where we have a Boolean formula in 3CNF, and we want to know whether this formula F is satisfiable or not. In the middle, we have a small example of a formula F in 3CNF, meaning we have clauses in conjunction, and every clause is a disjunction of 3 literals, and in fact this formula is satisfiable. And 3SAT is NP complete, but the concrete hardness of a concrete instance depends on the ratio of clauses and variables. And we choose 3SAT because it is very well known and well researched, and there are a lot of industry related use cases of 3SAT already today. It's quite an important problem. Then we said we want to solve 3SAT with a quantum annealer, so we have to reduce it to the native problem, the QUBO function. So what is actually this QUBO function, or QUBO problem? It's the problem of quadratic unconstrained binary optimization, where we have a target function, a binary target function with binary variables x and real coefficients c, and we can connect two binary variables, which is where the term quadratic comes from. And we are interested in an assignment x, which minimizes this target function. Then now that it is also possible to represent such a QUBO function with a graph-like structure, where the binary variables x are the nodes, and the connections between binary variables are the edge weights, the edges between nodes, and the real coefficients are either edge or node weights. This will become important later. Then when we want to use real quantum annealers, now we have some real life limitations. The two main important ones are, of course, the number of qubits and also the connectivity of the qubits, because if we look at our mathematical definition, we are free and we can't use as many variables as we want, and they could even be fully connected, which is not possible on a real hardware. Okay, so but how do we actually reduce our 3SAT function, our Boolean function, to a QUBO function? There's this very well-known Choi standard reduction, or also called the MIS reduction, because it in fact solves the maximal independent set problem on this QUBO graph. And the important thing to note here is the overall resulting structure of these QUBO graphs is that we get fully connected subgraphs for each clause, and conflicting literals are connected with the edge. And in fact, every literal has to be connected to all of its conflicting counterparts, which then will lead to a highly connected QUBO graph. And we also already heard that connectivity is a limiting factor, so this may be problematic. Now, the logical QUBO function needs to be embedded on the real hardware graph. And in fact, the whole process of embedding, we don't have to do this ourselves. There are tools provided by D-Wave, but we will benefit from understanding how this process works. So here we can see the structure of the D-Wave hardware graph, which is in real life obviously a lot bigger, but the structure is the same. And the two main things to remember here are that each qubit is connected to at most 6 other qubits. So there's the limitation in the connectivity, and the connections are limited to local neighbors. So we don't have global connections spanning the whole graph structure. Then what is this embedding? So say we want to embed a QUBO, here our ABC QUBO on the left, and even with such small QUBOs, we quickly run into problems where we have to split up a variable, here it is A, up to multiple nodes on the hardware graph, and these nodes then have to act as a logical unit. And these logical units are called chains, and they can get quite long and quite big. And of course, this is a waste of qubits, which we want to, which we don't want to. And also long chains tend to break, and breaking chains don't act as a logical unit anymore, and this leads to a loss of accuracy in our results, which is also bad. So we know now that the connectivity is really a limiting factor, but we have a reduction which leads to highly connected subgraphs, QUBO-graphs, and we want to reduce the overall connectivity of this graph. So by introducing a backbone with variable nodes, we can now connect each literal just only to its corresponding variable node, and this leads to the literals being connected to only 3 other nodes, and which leads then in overall to a much less connected QUBO graph. So great, now we have 2 reductions, but we don't really know which one we should use, which one is better. Both are mathematically sound. The MIS reduction has less variables in it, so this could be important. And the backbone reduction has less connections, but we can't really say which one is preferable. And the problem is that a net analytical analysis of these QUBOs is quite hard, and due to this embedding process, it also depends on the used hardware. So the easiest way to now compare these is doing it experimentally, and we use the D-Wave platform in this case, generated random 3-set instances with different clause variable ratios, or also different hardness of the 3-set instances, and played around with the hardware, D-Wave hardware parameters. Then we want to look at our results here in the slide. We mainly targeted the embeddability of our reduction, so we will look at this first. And here we have at the x-axis, we have the clause variable ratio, or you could also say the hardness of the such instances. The MIS reduction is blue and the backbone reduction is red. And in the top graph, we have the number of physical qubits after embedding, which is the really important figure here, because this is the number. This is the number of qubits we really need to solve the problem. And we can see even if the MIS method has less variables after embedding, the backbone method needs fewer physical qubits on the actual hardware graph. And the interesting part is that this strictly correlates with our chain length of the reduction, of our mean chain length. So we saved a lot of qubits because we avoided building long chains, which then from which we can expect that we also get a higher accuracy in our results, because, as already mentioned, the long chains tend to break and impose errors and lead to inaccuracy. So then let's have a look at the accuracy of our both of our methods. Here we have the probability of finding satisfying assignment for our SAT instances with respect to the hardness or the clause variable ratio, and the dashed line, the dashed curve would be the optimal curve. So this is the relative amount of satisfiable instances, and we want to get as close as possible to this dashed curve. And we can see on the top we have the MIS method, and on the bottom we have the backbone method, and we can see this. Yes, we really get a better accuracy in our results, where we get much closer to this optimal curve, which is very nice. And now we know that in both metrics, in the embeddability and the accuracy, our backbone method outperforms the MIS method on this specific setup, which we have experimented. So we should, on this setup at least, use the backbone method. Then to get to a conclusion, from an interface standpoint of view, it is we have a clear interface to our quantum annealing software components, and it is very easy to swap out quantum annealing software components and classical constraint solvers, because they have such similar interfaces. But at least for now, on the current state of the hardware, developers should keep an eye on hardware details, because hardware tailored optimizations can still lead to significant performance boosts. And then also about the experimental or empirical analysis, it currently is the best way of analyzing reductions, and therefore it should be a part of the testing and verification phase if one uses quantum annealing software components in his software architecture. Then this was it for me. Yeah, thank you for your attention, and I'm happy to answer any questions.
Yeah. Are there any questions? Let me just check also Slack. Yet. Okay, are there any questions to Tom? Either Tom, and Wolfgang is also here.
Yes.
So one of the things that you just mentioned is that developers should keep an eye for details. As you start building this, was it a difficult learning curve? I mean, is it difficult to take a classical problem, and just map it into the quantum world? Can you just say words about that?
Yes, I think the advantage of these quantum annealers is that our interface is strictly mathematical with this QUBO function, and this is not quantum at all. So you don't have to think about much about the quantum properties. If you just want to reduce a problem to this QUBO function, this is something I think most computer scientists should be more or less familiar with and have experience. So this is a great advantage, and it is also very similar to if you using, let's say, a simulated annealing solver, where you also have a target function and have to reduce your problem to the target function. So that is not that hard, I think, for someone without much quantum knowledge.
Oh, I see.
But it is easy to or there's a pitfall to rely on this clear mathematical interface and forget about the underlying hardware constraints.
Right.
So that is what I meant with the details are still
But
important.
then what are these, you know, these things that developers should keep an eye for these details? What are the main, you know, the main key concerns there for when you are building such a, you know, you are encoding such a problem? What are the, you know, the key characteristics that one should take into account?
Mm-hmm. Yeah. Well, as I already mentioned, you don't really have to do the embedding for yourself,
Mm-hmm.
but you have quite restricted hardware graphs, hardware structures, and the embedding if you can if you think about this, the limitations of your current hardware structure when you are designing the reduction, as we did, because we designed a new reduction with less connectivity and less global connections, you can help the embedding process to find better solutions or better embeddings on your hardware.
Mm-hmm. Okay.
So
Yeah.
Yeah, hope this answers your question.
Yeah. Yeah. And
can I also ask a question?
Yes, please.
Okay, so thanks for the talk. So you might have mentioned it, but I missed it. There was a point when I was a bit distracted. I'm sorry about that. But the way I feel it is when you're writing this sort of QUBO functions or this quadratic equation, somehow the precision of the coefficients, and you had that explicitly in one slide, is key to, and in my perspective, I might be wrong, but please confirm.
Yes, it is. It's definitely important.
Yes, and
I don't really talk about it because in our case, in our SAT, in our QUBO backbone method, we don't really focus on it a lot. But if you have other, I think with SAT it is not that important because we have a quite our problem is quite discrete, and we only have Boolean values in our target, in our real problem with our SAT function. But if you say you want to, let's take the traveling sales problem where you have real edge costs, then of course if you have two edges with quite similar costs, this imprecision in the coefficients can be troublesome. Yes.
Okay.
Actually, I can also make a little comment on that because we did the diff. So it turns out that the precision actually is not that important. We recently did a paper on that that investigated basically when we have a large QUBO, we can eliminate some of the smaller entries, say, because they don't bring much influence anyway. And it turns out that this is actually the case. So these QUBO problems are astonishingly robust to deleting less important entries. And so, of course, the coefficient precision is limited on current hardware, and you can find effects from that limitation, but that's not the dominant thing.
Okay. Yeah, great. No, thank you.
Wolfgang, you have raised your hand before.
Yeah, so I lower that back again. Actually, what I just wanted to make a comment on the on how hard it is to find QUBO formulations for industrial problems. So, as you know, I have an academic hat and an industrial hat, and the say patience and tolerance in industry for reformulating problems so that they fit on whatever form of quantum computer is approximately 0. So you should all keep that in mind, and that's why we chose SAT as base problem, and initially wanted to investigate how hard it is to replace traditional SAT solvers then with quantum-based SAT solvers, and compare performances and see how well that integrates with software architectures. But then we came across this thing that it doesn't really make sense to do comparisons at the current states of the art by just replacing components, because you still need to get into the details But at least as far experience inside Siemens, I cannot talk for other companies, of course, goes, if you have a solution that requires to change anything in your classical code, then people will most likely desk reject your ideas and not even try them.
Yeah, exactly. I agree with you. All right. Are there any other questions, comments? If not, let's thank Tom again, virtually, of course. Thank you, Tom, and Wolfgang, of course, for the talk. Now we move to the second paper.